So in this problem it says a beam of light in air is incident at 30 degrees on glass. And so I'm going to call this N1 and N2 rather than N for air and N for glass. And so I'm going to draw a picture of this and say, look, well, I didn't do that very well. Let me try again. There we go. And we're going to say that's theta 1 equals 30 degrees. And so since this has a higher index of refraction, I know it's bent towards the perpendicular. It's refracted this way, and so we're going to look at theta 2 equals question mark. Right, and that's the thing we want to find. Well, it turns out to do this, you need to know something called Snell's law. Willibrord Snell lived in the 1600s, and he found a relationship between light that's the incident angle and the refracted angle and the two indices of refraction. And Snell's law is this: it's N1 sine theta 1 is equal to N2 sine theta 2. That is to say, the product of the index of refraction and the sine of the incident angle is equal to the product of the incident index of refraction and the refracted angle. And so in our example, N1 is just 1, and so this gives us sine of theta 1 is equal to N2 sine of theta 2. So we're looking for this angle, right? And so we're going to say sine of theta 2 is equal to sine of theta 1 over N2. And so that theta 2 is equal to sine inverse of sine of theta 1 over N2. And that's equal to sine inverse of, so the sine of 30 degrees is 0.5, divided by 2 is 0.25. And so if I use my calculator, I can say, I can take the inverse sine, 0.25, and I get about theta 2 is equal to 14.5 degrees. And so, and it's consistent with what I see. I get 14.5 degrees roughly for that. The angle is bent towards the perpendicular when it's going from a lower index of refraction to a higher index of refraction. And that's Snell's law. In France, they called it Descartes' law because René Descartes figured it out sometime around the same time as Mr. Snell did. So here's another Snell's law problem. A beam of light in a material with an index of refraction N1 equals 1.25 is incident at 51 degrees on a material with index of refraction of 1.66. What is the angle of refraction? And so this is a similar problem, except we don't have a 1 here anymore. And once again, we use Snell's law. And so N1 sine theta 1 is equal to N2 sine theta 2. And that means sine of theta 2 is equal to N1 sine theta 1 over N2. Or let's just we'll solve it a little bit at a time. So we can say this is 1.25 times the sine of 51 degrees divided by 1.66, and what I get for that is 0.585. And so that means theta 2 equals sine inverse of 0.585. And what I get for that is about 36 degrees. So this is an experiment for studying refraction. This has just got angles written around it. This is just a sheet of paper. And then this is a piece of acrylic shaped like a half circle. And so the light enters from the laser, the light enters the circle and gets refracted along the direction that you see in this picture. And so in here, in this drawing, theta incident is equal to 30 degrees. We'll call that theta 1 maybe. And then theta 2 is, I'm going to call that 19 degrees. Why is this not 30? So I've moved the angle of the laser from 90 degrees over to, it's on the 60 degree mark, but the angle of incidence is relative to the perpendicular. So this is theta 1 equals 30 degrees, right? So N1, in this case, is just 1, because N1 is air, right? And so the incident angle is, this laser light is in air, and then it gets into this acrylic, and then it's got a different angle of refraction. And so we're going to use this arrangement and Snell's law to determine the angle of refraction. To determine the index of refraction here. And so you can see the laser light. It comes in straight and it gets bent because it goes into a material with greater incidence of refraction. Notice, by the way, that the reflected angle is the same as the incident angle. This is a demonstration of the law of reflection. That is to say, it's 30 degrees coming in, 30 degrees going out. The ray is partially reflected at the surface, and then part of it goes on through. And since it's hitting at the center of this half circle, that means it's hitting perpendicular when it gets to the edge of the circle, like all radii do. And so it goes straight on out and allows us to measure the angle. And so if we wanted to write down Snell's law, I'll have to write it small to fit in this little section that's off the sheet. I would say N1 sine theta 1 is equal to N2 sine theta 2, where here's my theta 1 up here, and down here is my theta 2. It's that angle, it's theta 2. I think I wrote on my sheet there. All right. Anyway, that's theta 1. And so we're looking for N2, and so N2 is equal to N1 sine theta 1 over sine theta 2. And that's just, N1 is just 1 because up there it's in air, so it's just sine of 30 degrees divided by sine of 19 degrees. And if I evaluate that, I get an index, excuse me, I get an index of refraction of 1.54. And so there are a couple other things to notice about this. I can bring this guy all the way around, and you'll see that as I get closer and closer to the grazing angle, more and more of the ray gets reflected than refracted, but it's still getting refracted, and you can still see that it gets bent more and more as it comes all the way down to the surface. Notice if I turn the system around and I send the ray in at the angle of the angle of refraction we had a minute ago, 19 degrees, it goes out at 30 on the other side, demonstrating the principle of reversibility of light, right? That if I just back the light up and send it in the opposite direction, it'll retrace its steps from the 19 degree mark over the 30 degree mark for, now this would be the angle of incidence and angle of refraction. And notice, by the way, that now since it's going from a material that travels slow to a material that travels fast, it's bending away from the perpendicular, not towards it. So there's some interesting stuff you can do here as I keep aiming it towards the center, but increasing the angle. You'll kind of see that I'm trying to keep it pointed roughly at the center. I'll get down over here. Let's say I send it in at 50 degrees, right? It's roughly at the right spot. It's going in at 50 and out at 50. Look at this. This ray, once again, it's getting bent away from the perpendicular. And so all of a sudden you'll see, I'll get over to here somewhere, and now, hang on a second. I've lost it. There we go. All right, hang on a second. So if I go right there, am I aimed at it almost? So it's hard for me to get, but notice that now the incident angle is about 40 degrees, and the refracted angle is almost 90. Right? And if I go much past that, and it's probably what you were seeing a second ago, it's almost gone. Now it's leaving straight along the surface, and then if I go any further than that, it disappears completely, right? And now we have total internal reflection, right? All of the light, there's no light that's escaping the surface over here, and all of it is being reflected internally. Right? So we can figure out the angle for which that happens based on the index of refraction we determined. So maybe I'll just leave that and say, look, in this case we have n1 sine theta 1 equals n2 sine theta 2. Now this side is our n1 inside the acrylic, and the air is our n2. And for n2, we're going to say theta 2 is 90 degrees. In other words, when we get it right along the edge of the surface, we call that the critical angle. Well, we don't call that the incident angle for which the outgoing ray is at 90 degrees is called the critical angle. And so this would say, look, n1 times the critical angle. This is to say, if I go anywhere past the critical angle, then I get total internal reflection. And so this says sine of theta critical is equal to n2 over n1, or theta critical is equal to the sine inverse of n2 over n1. Right? And in our case, that means theta critical is the inverse sine of n2 is this side, it's air, of 1 over, what did we say that was, 1.54. And so I can evaluate that with my calculator. And lo and behold, I get 40.5 degrees, which is about where we are. This is 90, so it's 80, 70, 60, 50. It's about a little, slightly over 40 degrees. That's the critical angle. That's where the refracted ray going from inside the glass or the acrylic to outside the acrylic can no longer happen. And so for incident angles greater than the critical angle, we get total internal reflection. And that's what you're seeing here. And so anywhere I go beyond that, the angle is completely, the light is kept completely inside the material. And by the way, this is how fiber optic cables work. You send the light inside a fiber optic cable, and then it's trapped. It can bounce inside between one wall and another, but it can't escape. It has no room, it has no way to get out of the tube that it's in, because it's shot in from the end. And so it has to stay in that tube, and so it can go all the way to California or whatever's really far away from wherever you're living.